Yes. Ah. Okay. Good. Uh, oh, that's strange. Well, let's see what we can do. I can tell you what's on the rest. Um, just transparent checkpoint restart, rethinking the HPC environment. Um, and so this is going to be a talk in two parts, supercomputers and then many cores on a single computer. This, by the way, is a really old netbook, so I think that's part of the issue here. This is the old 32-bit netbook. But in case checkpointing for HPC, and I'm going to talk about the two extremes. On one extreme, where we want to target supercomputing now, obviously MVAPICH is a very attractive target for us. And at the other end, just on a single main core computer. Uh, and there we're going to talk about something which I call a batch pool. If that works well, then we can go from a batch queue to a batch pool for a single computer, and eventually then to parallel queues. And with parallel queues, then we can bring back MVAPICH. So in fact, both topics really do relate to MVAPICH. So, the TCP, let me see if I can do a little bit of this. Exactly, yeah. So,
Can you cycle through resolutions?
I'd rather not play with it right now, but I think this should make it reasonable. So let's see, resize it a little more. Looks like.
Just a PDF?
Yeah. Um, okay. Yeah. Um, good. Excellent. So. Okay. Okay. Okay, close enough. Yeah. One more slide of tuning. I think that's really good. Okay, so as I said, two parts, supercomputers and many cores on a single computer. Um, so at this point, this is using DMTCP. DMTCP is a project that's been around for maybe 12 years or so, if you trace it back to its origins. It's actually fairly widely used. But first, let's just introduce it. Provides transparent checkpointing, so you don't have to modify your application at all. Uh, and you don't have to modify the operating system, no runtime. You don't worry about the runtime libraries, it just works. No kernel modules to worry about. We actually have portability across MPIs because we're working down the system calls. So, because MVAPICH is so advanced, we like to test on MVAPICH, but then what works for MVAPICH should work with other MPIs. It's based on standards So at the level of the deposit system call the Linux product file system, but also we don't go any lower than that, so we don't have to modify any existing libraries. The FTCP works on any language because it's working at the binary level. And then since 2014, we now are supporting InfiniBand, and because we're supporting InfiniBand, we can support PCAS languages. And we've actually tested on UPC, but in principle, it should work with just as well with the other PCAS languages. Um, so, um, so again, that gives us some idea of the philosophy. Um, Next, if it does work on PCAS languages, in principle, I would expect it to work with MVAPICH, MVAPICH 2X, although we haven't actually tried it. As for Intel Mike, hopefully it'll work next year. The current generation of Mike has the Mike chip on the door component, but certainly as of the end of this year, the Mike chip will be directly on the motherboard. At that point, there's this network between the door part and the motherboard that would just go away. In principle, we could have supported this extra Intel network, but they announced that it's sort of away in here. We decided not to put it the effort to support it. Okay, so then okay, so as I said, plug in two parts. Part one, we're going to talk about plugins. I just want to get a rough idea of plugins. The reason why plugins are so important is that if you look at the different dimensions which we have to support, if we're going to support HPC computations, there are major API implementations. We want to work across all of them. There are different resource managers. We should be able to support each of them. And each of those has its own peculiarities. Different process managers, which are used to support API and runtime. Again, we need to, and those tend to be separate processes that you also have to checkpoint while the process on each computer node. Different networks, InfiniBand and sockets we certainly support, and we expect to be able to support newer APIs since these are representative of the main ones already made, and for sockets, we're going to see more traditional, for example, Ethernet-based networks. Other computational models, PCAS, you get that free where you have InfiniBand. Okay, so let's continue. This will come back to later. This is about what I briefly said, replacing a batch queue by a batch pool. Rather than go into details, the main idea here is if you can checkpoint jobs, then want to take every single job in your batch queue, start each one of them running and checkpoint it, and put it into a single pool. Now there's in a pool you can run in any order. That's great, that gives you more flexibility. Can you discover which job should be run simultaneously at the same time without interfering with each other? Well, it turns out if you can checkpoint and restart, you can discover the characteristics of the jobs at every time, and then you can mix and match. We'll talk about that briefly at the end of this talk. So, so this point, checkpoint, we're going to talk about plugins for supercomputing. There is a talk tomorrow which I want to advertise at the end of tomorrow's session, transparent checkpointing for supercomputing. That's where you see some of the latest numbers that we're getting and some of the specific techniques that we're using, but this is meant to be more of the general philosophy. So first, just a short demo, that's why I use this netbook. So this netbook has specs in older one. It's approximately 10 times slower than any computer you can imagine today. But it doesn't even have 64-bit RAM. But nevertheless, I want to show you that works reasonably. They say the picture is worth 1,000 words. So normally I was leery about putting a demo, but in this case, I'm hoping that the demo will be worth 1,000 words. Okay, here we are. So here are the files. We have this file. It's going to be our example plugin. So we're going to modify the sleep system calls since we're operating at a level of classic system calls. And we're also going to change it what happens when you write a checkpoint or when you resume. So what is it we do? First, we go to compile it to build the libdmtcp sleep1.so. That creates the library for us. Here's the library in green, so almost unreadable, but it's a .so library. Now we're ready to run it. And to run it, let's move this up. To run it, we're just going to take out the launcher, the MTCP launch, and we're going to run it with the plugin libdmtcp sleep1.so. We're going to run it on a standard application. In this case, as for my standard application, I chose a really stupid one that just knows how to count. So you're just counting 1, 2, 3, and it does sleep in between each one of those. So let's watch what happens when we run it with the plugin. So again, with the plugin, it's going to run like this. Okay, and slowly coming off the screen, there you see. So this plugin is going to announce that we're in the middle of a sleep call. When we finally hit a checkpoint, it announces that we're doing the checkpoint, it announces the resuming. It all works. And it's code trivial. How do we do this? It took us 42 lines. It took us 42 lines of code, and that's including comments as an example to other people. Plugins should be independent of each other, and they are. So let's run it now with 2 plugins. So again, it's going to have to come up the screen. Here we go. So here we see Sleep 1 and Sleep 2. Sleep 2 is the inner plugin, Sleep 1 is the outer plugin. When the checkpoint, they both record. And then finally, you would expect things like application initiated checkpointing. Application initiated checkpointing works, and it's very easy. So this will be our application. So in here we have a routine called main, and in that routine called main will include the mtcp.h, but that's all. So therefore, this executable run with or without the mtcp, it doesn't matter. And the first thing to check is simply, is the mtcp enabled? So let's make it. Now we have an application. When we run it by itself, it says the executable seems to not be enabled. So now let's run it with the TCP. And of course now it reports that yes, the probe is enabled. And furthermore, we can checkpoint resume. Okay, so you're not the demo. Let's go back to the slides. But hopefully by this, what I tried to convince you is that everything is very easy. Again, the only code behind this demo was sharp include dmtcp.h, and that immediately gives us these functions. The MTCP is enabled, the MTCP checkpoint. We can always check return values, and if the MTCP is not present, the return value just tells us that. So we have the same executable, we don't have to recompile or relink. Okay, good. Now, coming back to the talk. So DHP is mature software, generous FAQ. There's among published literature, you see 40 other groups that have published in the literature how they use the TCP. So it's reasonably widely used. Not as much as MVAPICH, but and here we see downloads, about 9,000 downloads. Again, not a quarter of a million, but we're a smaller group. So it's the MTCP forum where we tend to now get perhaps 25 or 30 questions and replies on the forum. So how does it work? Well, again, I won't really stop for details here. We do want to think about bidder. But in case we're using this thing called LD preload, which preloads our library, and our library gets to execute before main. Because our library gets to execute before main, that means that when the application starts up, our library is going to create an extra checkpoint thread that can spy on what's going on. When it's time to checkpoint, the coordinator will send a checkpoint message down. Our checkpoint thread will send a signal by default to user 2 to each user thread. The user thread now is forced into a signal handler, but in fact our library wrote that signal handler. So our library then stops them. Now the user threads are not doing anything. Memory is stable. Once memory is stable, we can just write more memory onto a file. Of course, there might be some data in a socket connection. After all, if we're going to checkpoint API, you expect this to work in a distributed scenario. So if there is data in the socket connection, again, there's a simple algorithm. Algorithm is too generous. So we usually call this drain the socket. Just set a special cookie down one end, at the set end and at the receive end, keep reading data until you see that cookie. Now you know there's no more data in that work. When you're ready to restart, send the data back to the sender puts the data back in the network, and then once the sender puts the data back in the network, we unblock the user threads, and we come out of the signal handler, and we continue exactly where we were. The secret is basically we're saving memory and then restoring memory exactly, bits or bits. Whatever memory was on a certain address before checkpoint, that same memory value will be on the same address on restart. So we don't care what the local libraries are doing, and hopefully we don't miss any difference either if the memory was identical. Okay, so that's the idea. This explains it in a little more detail, but that's the idea. Why plugins? I will stop. I took some time to demo, so I just hope that you believe that plugins are useful. Here's one way in which we do use plugins, though. This will give you some insight in how to use the plugins effectively, given that we are providing them already. So if you want to use them effectively, one of the really nice things is you can use them to virtualize. You can virtualize almost anything. Process IDs, network addresses. That's why we can checkpoint on one cluster and restart on a completely different cluster, and so on. So what do we mean by using plugins for virtualization? Hopefully this diagram is almost self-explanatory. Our plugin sits here at the interface because we work at the level of system calls and library calls. So if the user process makes a call to kill, first the user process calls get PID. The process ID is 2652. We tell them it's 4000. Never let the user know their real PID. Don't create trouble. Later they decide, okay, I want to kill process ID 4001. No problem. We have our translation table. We'll translate between real and virtual and make the right thing happen. Now it's time to the checkpoint, then we restart. When we restart, the kernel gives us completely different real PIDs. They're different, they're not even the same. No problem. At the time that we restart, what should we do? Well, just ask the kernel what are new process IDs, update this table, and if you do not have to update the user process, that's the secret of virtualization. Never try to update the user process. Just update the plugin that's aware of checkpoint restart. And the user process should be ignorant of any checkpoint or restart. Good. Let's see. More details, but I won't stop to talk about that. As you'd expect, we have a library of a few plugins right now. Maybe the InfiniBand plugin is one of the most interesting ones to talk about here. So InfiniBand plugin, this was presented in HPC in the year 2014, a little over a year ago, or the work was done more than a year ago. And then once we checkpoint over InfiniBand, that's finally when we're ready to start thinking about supercomputing. Until then, We just weren't ready. The other thing that I'm hoping is that supercomputers will switch from back-end storage to mobile SSDs. At that point, full memory dumps become more effective. So here we go. We have a InfiniBand plugin. We can checkpoint while the network is running. The older strategy said take down the network. Now you have single process dates on each node. Checkpoint your single process using an older checkpointing package. When it's time to restart, and rebuild the network. But that takes extra time. We don't have to. We don't have to take down the network and rebuild it. Furthermore, we designed the plugin based on the API. So this is the business of intercepting system calls and library calls. In this case, we'll be intercepting calls to the InfiniBand library. And we don't care which vendor wrote the InfiniBand library because the API, in this case, the O3B, stays the same across vendors. If a vendor announces a different API, then we do have to provide a modified plugin in that case. But hopefully, with similar functionality, once we have the first plugin, it's easy to do a second one. Okay, so what's difficult about virtualizing InfiniBand? Why did it take us so long? Well, they have these queues: set queue, completion queue, receive queue. They're hardware. When it's time to checkpoint, it would be nice to just go to the hardware and save their state. That's not so easy. Luckily, the API does tell us that we can pull the queue and find what's in it. Unfortunately, the API says that if you pull that hardware queue, you're going to destroy what's in it. We'll give you what's in it, but it won't be inside anymore. So therefore, at restart time, we have to put it back in. So putting it back in is really a pain. What we do in order to get around this is we basically create a shadow data structure. And now the user code talks only to the shadow data structure, and we decide what parts of the shadow data structure can copy into the real data structure. In particular, the shadow data structure will have our own portion of the queue, and we can prepend to this queue. So at checkpoint time, we destroy what was in those queues. So up here, these queues. Anything there gets destroyed. But at restart time, we'll take out a copy of what used to be there. We put it into here, and this now gets prepended to the actual hardware queues. And now, when the user goes through the API to ask for anything from this queue, first we exhaust our virtual queue before we turn things over to the hardware queue. So that's a more sophisticated example of virtualization. But once you realize that these strategies are possible, it's hard to say where to stop it. It really applies over a variety of cases. I'm not going to talk about the others, but just say all others. Here's a batch queue plugin, plugin for checkpoint in a virtual machine, a plugin for checkpoint in a network of virtual machines, plugin for checkpoint in 3D graphics. If you have a GPU that is used not for GPU computing, but for what it was originally intended for, 3D graphics, we can checkpoint it. In this case, we can even do it in a very independent way. Again, because the API of the OpenGL stays fixed, and we build plugin into the API, not against the vendor's implementation. Okay, so and we have other collaborations. You can use this to support cloud computing, where you can checkpoint and restart at the process level instead of the virtual machine level. There's work starting now on big data. Can you checkpoint Epi and do computation? Suppose some high priority heavy computation comes in. Maybe what we propose to do here is to suspend the original computation, save on the back end the data files associated with the original computation, checkpoint on the front end, and now start a new job. Later, when the high priority job is finished, we will bring back the low priority job. On the front end, we will restart. On the back end, we'll bring back the intermediate files and storage. so everything is efficient. We don't have to copy large data. Hardware as a service, there's really no time to talk about here. That's just starting, but that's with the Massachusetts Open Cloud. And in this case, the idea is how long should it take to switch from one Linux stack to another? Ideally, we'd like to do that in about a second. How do we do it in a second? Well, there's this new feature of KSec in Linux kernel, which allows you to quickly change from one Linux kernel to another Linux kernel. But that's only half of the other half of the is the init process and all the daemons and starts. But if you can checkpoint the init process, then maybe you're good. So that's the plan, but again, that's a project that's just starting. So hopefully I showed you that this is a fairly general strategy. And now I'll show you one of our newest projects where we're applying this. So this is, as I said, WorkMatch Rules. So people talk about many-core computers. That's the number of CPU cores keeps doubling every so often. Traditionally, it would be a batch queue. If it's for a single computer, there would be one queue. But as I said, we can now take each of the jobs in that batch queue, start them up until they pass the initialization phase and reach some steady state, checkpoint them. Now we have a pool of checkpoint images instead of a queue of executables. So if you have a pool of checkpoint images instead of a queue of executables, what can you do with that? That's different. So what you can do is, so again, this is more or less saying what I just told you. And what I'm arguing here is we're entering the era of many-core computers, and yet we're leaving the spare CPU cycles and just pulling on the floor because we don't always know how to keep all of the cores used at the same time. If you have 32 cores, there's a good chance that some of those CPU cycles are just going to fall on the floor, as they say. Can we design a more efficient queue that makes sure to use all the spare CPU cycles? So, and this is in a diagram which more or less says what I just said. Part of what we'd like to do, in fact, is we'd like to overcommit CPU cores. Right now, typically, if you're using a popular resource manager, they'll ask you how many cores do you wish to reserve, and they'll give you exclusive use of those cores. What that means is you now need to overestimate how many cores you need, because you must specify the number of cores you need at the phase where you're using the maximum, where you have maximum requirements. There may be other phases where you're not using all of those cores. Can somebody else use those cores during those other phases? The answer is yes, if you design it right. With checkpoint and restart, you can suspend some jobs and bring in other combinations. You can now bring in other jobs that can use the extra cores that temporarily your job is not using. How do you plan to do this? So, well, we need to match compatible jobs. A good example would be mixing a CPU-bound job with a RAM-bound job. Those two coexist quite nicely, and then we can now overcommit. How are we going to do this? Well, we need to measure the throughput. So measure the throughput as the number of instructions per second divided by the number of CPU cycles per second. And of course, the machine dispatch registers will give that to us. Okay, so at that point, again, this is going into some detail about how to propose to do it. I just want to hit the highlights. I don't want to take too long. So ultimately, we're going to periodically rebalance which jobs in the batch pool will execute. When we rebalance, we'll just checkpoint all of the currently running jobs. Now, everything is in the pool. Since everything is in the pool, we just got a bunch of checkpoint images. For those checkpoint images, let's measure the characteristics of each one, because each job might now be in a different phase. where its running characteristics might be a little different. It might be floating point intensive, RAM intensive, whatever. But using things like machine state registers, you can estimate what resources it's using. So get the estimates for each job individually. Now we need some algorithm to propose a combination of jobs. Run those bit of combinations in parallel, pick the best combination. So test each one, pick the best combination, and then that's the one that goes live. So as we say in step 5, select the winning candidate and execute it until the next time go. Good. Okay, so now there's one thing that was we punted on. How are we going to propose the combinations of jobs that should be good candidates? If we only propose a small number of candidates, it's easy to test them one by one and decide which one is the winning candidate, which one will have the best throughput. But if we're only going to propose 10 candidates and we have 50 jobs waiting in our pool, there are something like 50 factorial combinations. We don't want to propose all combinations. So that's where we're going to delegate. We're going to delegate using autonomic computing. I won't really stop to talk about autonomic computing, but this involves a collaboration we have with Saeed Tazi and Lux in France, who's at Lux in the University of Toulouse, where we also have an IDEX appointment that we discussed. So that's the continuing collaboration. The plan is to use autonomic computing. The knowledge base is the set of rules that will be used. How will it get used? Well, the idea of autonomic computing, maybe I should go back up again. The idea of autonomic computing is an analogy with an autonomic nervous system. The brain provides the platform control. The local processes are controlled autonomously using knowledge from the brain. So who is the brain here, and who is the local process? Well, in this case, the system administrator is up to the brain, and the system administrator sets the high locals. Things like how much energy we're using, absolute relative job priorities, high throughput versus good energy use, software hard deadlines, fairness policies. These are all things that systems administrators would be familiar with. What are some of the low-level issues? Measuring the throughput, limiting cores, worrying about core affinity, worrying about turning hyperthreading on or off, and tricks where you can actually turn it on or off per core effectively, because two virtual cores will be paired. And if you don't use one of these virtual cores, it's almost the same thing as turning off hyperthreading on it for that pair of cores. Aging. So we can worry about these things while the system administrator worries about the high-level stuff. So that's the plan. We're already, I would say, halfway through on trying to implement this. Time will tell how it works. So good. Hope to stay to my half hour, include the demo. And any questions?
Any questions?
So I have two questions. One, for the MVAPICH checkpointing, who's checkpointing the shared memory segments?
We are. There's another plugin which I didn't discuss, but it's called the shared memory plugin. It's responsible for figuring that out. I briefly describe the algorithm. At the time of checkpoint, we discover which segments are in shared memory. That's easy using things like the POP system. At the time of checkpoint, we elect a leader of process for each shared memory segment. Now at the time of restart, we remember who was the leader because we just restored memory exactly the way it used to be. So if we know who was the leader, the job of the leader is to look at its memory at the shared memory segment and write out the backing file. Now that the leader has written out that backing file, we hit a global barrier. Now it's the responsibility for everybody who's not the leader to map that back in. then we hit another barrier, and at that barrier we now delete the backing particle, assuming you want shared memory, anonymous shared memory. And now we have created the semantic equivalent of the shared memory that used to exist. It's not literally the same, but it's semantically equivalent, and this again is in the spirit of virtualization.
Okay, so my second question is, like as we are adding more and more features to the stack overall, especially when you're emulating the access to the queues, um, it kind of raises the question of what is there any performance degradation that might happen, or like have you done any performance studies in the non-fault case?
Yeah, so for performance studies, especially, you should ask Rohan, who will be presenting tomorrow, where we've done specific studies. But what I will say is that there are essentially two kinds of overhead to worry about. One is during normal runtime, and the other is during checkpoint restart. During normal runtime, most of what we're doing is putting a very thin wrapper around the library call, which typically is doing something like doing the translation in that translation table that you saw in the example of the IDs. So at runtime, we experience almost zero overhead. There is an exception to that with the current InfiniBand plugin. We know the cause is we fixed it, but all the other plugins, and so for the InfiniBand plugin, we're seeing 1.7% overhead. But for the other plugins, it's much less than 1.7%. And then there's the checkpoint restart overhead, and those can take anywhere from less than a second to, well, you see the numbers tomorrow, on the order of 20 or 30 seconds. Yeah, so it's again, reasonable scale, but wait for tomorrow's talk and you'll see the details.
Any other questions? Yeah.
Okay, so let's go there. No.
Why don't you go ahead? Oh, okay.
Go ahead. Okay. The conversion table for virtual PIDs, where exactly is it kept?
So each plugin is a separate dynamic library or .so, just like in the demo. A library has both text or code and also data. So we just keep it in the data segment of that library. We don't have to worry about data structures. It's just a struct in memory. And since bits are bits, it will look the same on restart as it looked at the time of checkpoint.
So what happens to the processes after, if something happens to that library or the node dies, for example, and it's no more, you don't have that table anymore?
So if we lose that library, so that library becomes part of our checkpoint image, because our checkpoint image is a copy of all of memory, including every library. So if we lose a library, that's equivalent to saying that we lost our checkpoint image.
Oh.
And then there are standard proposed solutions in the literature, such as redundant copies and so on.
Thank you.
Dr. Cooperman, I have two questions actually. First one is just want to make sure the InfiniBand plugin, like you just mentioned before, there's no any change to the InfiniBand driver, right?
Exactly. That's very important for us. We try to never change anything outside of the, well, we never change anything literally. The user code, the binary, the libraries, nothing changes. No kernel modules. We're just adding extra libraries on top of it. That's the only thing we do.
Okay, and then the second question is, when things come to the SRV, suppose I launch one VM on one node and use the pass-through one virtual functions there, and then migrate to another node and try to have another virtual functions pass to it. And your InfiniBand plugin can handle this?
It can. I'll say there are two answers to this question. The first answer is as long as it's a homogeneous cluster in the sense that they use the same InfiniBand driver, then yes, it just works. Currently, we don't support heterogeneous InfiniBand drivers. We know how to fix that. But here's the issue why supporting heterogeneous drivers is a little more difficult. If you have heterogeneous drivers, that means that you have one MPI process here using one library from one vendor, and you have another MPI process here using a different InfiniBand library from a different vendor. Now we restart. We put this library from this vendor over on the hardware from the first vendor, and now there's a clash. It doesn't quite work. The solution to this, which we have not implemented at this time, would be to, at restart time, our plugin should detect at restart time that there's a conflict. Our plugin should then locate what is the address at which this library is loaded. Our plugin should then unload this library and load in the library of the other vendor. When we do that, of course, we then have to initialize the library of the other vendor also. And then but that's okay. Initializing the library is no problem because we're going to start with empty queues for InfiniBand, and then we deposit that back in the queues. So in principle, we can also cover the case of heterogeneous, but we find that the typical HPC center has homogeneous InfiniBand, and so we have not put our resources into the heterogeneous case.
Thank you.
Any other questions? Okay, otherwise we'll start. Okay, so I think we're almost finishing. So I think the last one, we have kept some time for open mic session. I know it's getting late, but let's spend a little bit of time. As I indicated in the morning, we typically use this session to get feedback from you. And I know, like today in the morning, Adam already